Okay, good morning. Welcome back. So today's first lecture is going to be of a different flavor than yesterday's. Yesterday's we gave you a bunch of details about hardware and the software tools so you can get started on the hands-on session. Today we're going to be more abstract and tell you about how to recognize certain patterns that I alluded to yesterday. So how do you recognize sources of parallelism and locality in the problem that you want to solve so you know which of those high-level patterns, which may have been solved already, you want to use? So let me tell you what parallelism and locality mean. They're both critical to importance. Parallelism for sure. How many things can you do at the same time? But what does locality mean? If you have two arguments, two numbers you want to add or subtract or compare, they have to be in the same place at the same time. Otherwise, you can't do anything with them. That's locality. So if they're in different parts of your machine, for example, if they're both in DRAM, you have to get them together to be in cache. The hardware will do that for you. Or if you're writing message passing code, you may have to move them to the same processor to have work done. Either way, doing that data movement to put them in the same place at the same time costs orders of magnitude more time and energy than actually doing the operation. And so if you don't get that right, if every time you need to do an operation you have to move a lot of data, it doesn't matter how much parallelism it is. You won't speed up. So you got to get both right. And so I'm going to talk today about how to recognize natural sources of both in a lot of simulations that come up naturally and patterns that will have solved that problem for you. And I'll go into more detail tomorrow about how to optimize some of the patterns inside, like linear algebra, for example, to minimize communication. Today we're just going to recognize it in a natural form. So the good thing is a lot of real-world problems have parallelism and locality just staring at you if you know what to find. So, for example, many objects move independently of one another. I mean, that's pretty obvious. Billiard balls rolling around. Each is guided by F equals MA. They don't have to talk to one another. They depend much more on nearby objects than distant ones. Again, billiard balls, it's not until they're really close in touch that they affect one another. Otherwise, they don't affect one another at all. And also, the dependence on distant objects can be simplified. Obviously, the farther away something is, the less gravitational force or electrostatic force it exerts on you. And it not only gets smaller, it gets simpler in certain ways. So you can approximate it and do a lot less computation and data movement. And indeed, particles moving under gravity are examples of all three, but these come up all the time. Then, when you actually take your model and you want to discretize it, replace time, which is continuous, by time steps, time equals 0, time equals 1, time equals 2. That introduces more parallelism and more opportunities for locality because information only moves at a finite rate, so you probably only have to talk to your nearest neighbors in a certain sense to get enough information to do the updating. And then many problems exhibit parallelism at multiple levels. And I'm going to use some EE examples, electrical engineering examples, but there are plenty of others as well. And so there are going to be 4 kinds of simulation I want to tell you about that come up all the time. They're sort of sorted in order from most discrete to most continuous. The first one is discrete event simulation, where everything is discrete. Time is discrete. The state is discrete. So the game of life, which you may have played a long time ago, it's a bunch of cells. Each one talks to its nearest neighbors, north, south, east, and west. And depending on whether they're alive or dead, it becomes alive or dead. So manufacturing systems, finance, they're discrete events where that happen, trades, there's discrete prices. Circuits can be simulated that way, digital circuits, and games. I'll use games as an example. So Pac-Man as an example. So the next kind of thing, I'm going to make it a little bit more continuous, introduce particle systems. So particles moving around, F equals MA, but there's still a discrete set of particles that are moving around. We're not simulating what's going on inside of them. Billiard balls, I already mentioned. Galaxies, atoms, circuits can be done this way. SPICE was invented here at Berkeley to do the simulations of this sort. And pinball is a yet fancier game. The next level, I'm going to make it a little bit more continuous because I'm not going to have a bunch of discrete objects moving around. I will have a finite number of parameters. I'm going to call those ordinary differential equations. That comes up all the time in structural mechanics, chemical kinetics, circuits. Again, I should have said that's where SPICE fits in. It can be modeled that way, can model at many different levels. And the next level of game is, which I will actually show you a demo of, is Star Wars, The Force Unleashed. And the final level is where everything becomes continuous. Time becomes continuous, space becomes continuous. Those are partial differential equations. And, many things you learn in physics work this way. Heat, elasticity, electrostatics. Somebody won a Nobel Prize for doing finance this way too. Finance happens at all different levels. And medical image analysis, and yet another, well, not game, but movie, which had our former governor in it, Terminator 3, Rise of the Machines. So, and I will give you these examples. So the point is, a given phenomenon can be modeled at multiple levels. Many simulations combine these techniques, and there is a particular interesting website I'll show you later on the game up here. The other important difference, at least locally important difference between this particular one, Star Wars, and Terminator 3, is that all this work on parallelizing it was done at Berkeley, and all this work was done at Stanford. But otherwise, they're both very interesting projects. So let me just talk about circuit simulation, just to give you a sense of how one problem has been solved many, many times, because it has to be, by doing modeling at many different levels. So here are the different levels at which you can think of a circuit, a digital circuit. You can think of individual instructions being executed. You know, that's the computer program that you see in front of you. You can think of it at the next level down at what happens cycle by cycle, because an instruction happens in many cycles. Then what happens in a cycle, you can worry about where the actual data is sitting. Then registers are built out of gates. Gates are built out of switches. Switches are built out of circuits. And then circuits are built out of little pieces of silicon with things moving around. So this also expresses that continuum I was telling you about, from most discrete getting more and more continuous. And people do these simulations at all different levels. And in this last column are the names of important both commercial and academic projects over many years that have done these simulations. And so depending on your problem, you may want to look at the same problem at different points of view. Okay, so the outline of the talk then is that I'm going to take these 4 different kinds of simulations, which is sorted in order from most discrete to most continuous, tell you at a high level how to recognize the parallelism, how to recognize the locality, and how to make them run as fast as possible, and sort of recognize common problems that span these different ones. The other thing I want to try to do is tell you how, tell you how the 13 dwarfs arise. I'll get back to the 13 dwarfs. Arise naturally in these different problems. So the example problem I'm going to use, and you're already doing one of them for your hands-on session, is called sharks and fish. We have built over a period of time baby problems that illustrate all those different levels of simulation by having an ocean full of sharks and fish that swim around, that have rules for who eats whom, and how they move around depending on the currents, and depending on whether a shark is attracted to a fish. So they're sort of simple models of everything on the previous slide. There's a bunch of different versions we've posted on the web page. We've made them available in lots of different languages so that you can sort of go play with them and see. We're doing one of them. We're just doing the particle simulation for the hands-on one. And so you can see all of these available. And so you're not going to be able to do all these in the time available for the hands-on session here. But when you go home, you may want to go back and try looking at these in these different languages and doing the different simulations. And the other goal, as I said, is that I'm going to try to show you where these 7 dwarfs that I mentioned in my very first talk yesterday come up naturally when you try to exploit the parallelism and locality in these different simulation problems. So I will just mention these. Today, I'm not going to tell you how to actually implement these quickly. Tomorrow, I'll try to do that, give you an overview, because there's a lot of stuff here. Okay, so let's start with discrete event systems. But before I go on, are there any questions about the general game plan? Okay. So what are discrete event systems? You got a finite set of variables. The set of all values at any particular fixed time is called a state. And you have rules. Each variable is updated by computing a transition function depending on the values of all the other states, and maybe an input, change the value of the state. And so you can think of a digital circuit as the canonical example of that. So there are 2 kinds of systems we have to worry about simulating. They can either be synchronous or asynchronous. In the synchronous case, there's discrete time steps, t equals 1, 2, 3, and things are only allowed to change. Everybody changes at the same time at those time steps. That's called a state machine. And the other case is that you only change when your input changes. And you don't know when that's going to be. It's not going to be necessarily every fixed time step. It could wait a long time, or it could be quite rapid. And that's called event-driven simulation. And you can imagine, that's more like the way the real world works, as opposed to, well, a digital circuit is the real world. But it's, there's a clock. There's not always a clock in the discrete systems that you want to simulate. And the example, that, again, it's on the web page, is the game of life. I'm going to divide space into a bunch of cells, two-dimensional cells, and there's rules that govern how each cell updates its value depending on all its 8 nearest neighbors. And so I'll just keep giving pointers to where this code lives. It's the third sharks and fish example. So let's try to solve that problem. Find parallelism in the game of life. And remember, so I have a two-dimensional grid, and every grid value is going to update itself depending on some rule that depends on its 8 nearest neighbors. So top, bottom, left, right, and the 4 corners. And so I need 2 copies of every data cell, the old one and the new one. And so all I have to do is grab the old values of my own and all my nearest neighbors and write my new value into the new copy. And so I take the old, it's read-only, write into the new, and then I switch their roles. I read from the new, write to the old. I just sort of ping-pong back and forth between these 2 ones. And it's very natural to be parallel. And so the question then becomes, how do I assign the work to all the processors? And the easy way to do this, it's perfectly natural, is a technique called domain decomposition. So suppose this square here represents my grid of my grid, 2 grids. It's my grid of points, so there's a very fine mesh of points which I haven't drawn. I want to assign them all to 9 processors labeled P1 through P9. And a perfectly natural way to do it is to assign every processor a little square of data points. So there's a whole bunch of data points inside P1. Every data point has to talk to its 8 neighbors. And so if you're in the middle, then all your neighbors are stored locally. Locality is satisfied. It's only when you're on the border that you might need to talk to the other processor who owns your nearest neighbor to get that data to update your value. So here's the loop. It's very simple. I'm going to repeat until I'm done simulating. I'm going to get my neighbor's data that's just along the borders. I will then do a barrier. Everybody stops so we all update at the same time. Nobody gets into a race condition. And I'll exchange the state with my neighbors, and then I do an update. And I just keep repeating that. So it's a very simple loop. And so how do I get locality to work? Well, every processor is going to get assigned as large a patch as I can. And I want it not to have to talk to its neighbors very much. So here I've done what seems reasonable. I've given everybody a square. But there are a lot of choices. How do I decide what's the best choice? In particular, if it's not a perfectly nice mesh like that. So let me just sort of talk about this one in a little bit more detail. So let's suppose I have a 2-dimensional mesh. Everybody's talking to, let's just suppose 4 neighbors, north, south, east, and west. And I want to think about different ways of partitioning it and ask which way minimizes the amount of data movement or maximizes locality. So here's my 18 by 18 mesh. Every data point is at the intersection of these 4 edges. And that edge means that guy depends on its 4 neighbors. So the question is, so I have an 18 by 18 mesh, and I want to assign it to 9 processors. Here are 2 natural ways to do it. I can assign 2 rows to each processor, so each color is indicated by a different processor. So that's one way I could divide up the work. And the other way is the way I just did it before. I divided up into squares. So let's count how much communication is required by these 2 perfectly natural ways to assign the data for the general case of n by n mesh assigned to p processors. And if you count how many of those edges, black lines, goes from one processor to another, from one color to another, it's proportional to n times p, roughly. So I'm just counting the number of black edges that cross from blue to green, from light green to dark green, and so forth. On this one, the number of edge crossings is proportional, you can do the counting, to n times the square root of p. That's a lot less, right? Obviously, that's preferable. And so in general, the intuition is that if I want to take this mesh, which could have an arbitrary shape, not just a perfect square like this, and assign it to processors, what I want to do is pick these shapes to minimize their surface to volume ratio, or in 2 dimensions, the perimeter to area, right? I want to have as much to do locally where I don't have to cross the border. So that means I want to minimize the size of the border. And here it's easy to see what to do, but if it's totally irregular, well, it's not so obvious. So here's a slightly, so let me talk now about synchronous circuits with that in mind. So what is a circuit? It's a circuit with a bunch of vertices which represent AND gates and OR gates. There are edges between them in the graph representing where the data moves. And so what I need to do is figure out how to divide up that circuit among a bunch of processors. And it's going to be done synchronously. That means I'm going to only change things when the clock ticks, so the time steps t equals 0, 1, 2, 3. And so what I need to do is take that potentially totally irregular graph, not a 2D mesh anymore, and assign it to a bunch of processors. So that problem is a well-studied problem. There's lots of good solutions to it. It's called graph partitioning. And so here I have a not so big irregular graph, but it makes the point. So there's 8 nodes and there's a bunch of edges. And I want to assign it to 4 processors, so I've drawn little boxes to indicate the assignments here, 2 different ways of doing it, and I want to pick the best way. And what are my goals? I want to make sure it's load balanced, so every processor has about an equal amount of work to do, so in this case 2 per processor. And I want to minimize the amount of data movement, maximize locality, which in this picture means minimize the number of edges that cross from one processor to another, because that's the work. Now, it turns out if you write this problem down as a mathematical problem and ask how to solve it, it's one of these famous problems that's called NP-hard. So that means, if you're a computer scientist, that the only way to get the best answer is to do something that's exponentially, ridiculously expensive. Nobody ever does it. So as a result, there's a lot of approximations that are quite sophisticated, and the good news is they've all been built into libraries that we can all call that are available. So you should this is one of those problems you should recognize as a reasonably well-solved problem. Not that research is over, but it's reasonably well solved. So in these 2 examples, which one is best? This one has 6 edge crossings, that one has 10. This one's better. Here you can do it by eyeball, but if you have thousands or millions of nodes in a graph, you're not going to do that by eyeball. Okay, so here is a slightly different version of it, which indicates the subtlety of it. So suppose that I have, imagine sharks and fish in loosely connected ponds. So I have just 4 fish in that one, 4 fish in that one. So how am I going to imagine parallelizing this? And so if I have edges, I don't have very many edges here, connecting this guy to that guy. It seems pretty clear that I ought to cut my graph there and assign all this to one processor, all that to one processor, and all that to one processor. But there's really not going to be much work crossing this very often, right? So it seems kind of silly to wait and send messages along these little borders every time step, right? Because probably nothing is going to be moving along that time step. This guy's going to run independently for a long time. This guy's going to run independently for a long time. So that brings us to the second style of simulation. Not synchronous anymore, but it's going to be asynchronous. So instead of doing something at every time step, the idea is to only bother updating your state when an event arrives sent to you by a neighbor, by a different processor. And so there's no global time steps, but individual events, updates, have to be timestamped, so you know when you made that decision. And so the example in the previous slide would have been each pond is going to go by itself for a while until the neighbor tells it something has happened. So you don't have to stop and do a communication every time step. Circuit simulation happens that way. You may not get a signal from another part of the circuit very often, so you just keep updating your part. And the same thing with traffic, right? Everybody kind of moves along, but the cars change lanes once in a while. In the meantime, you just keep simulating along. So this is going to be potentially much more efficient because there's many, many fewer messages, but it's going to be a lot harder to parallelize. So you can imagine, if you're writing MPI code, message passing code, which you sort of heard about yesterday, you'll hear more later today. How do you know when to ask your neighbor for a message, right? When do you do a receive? So there are questions about how to implement this. So the question is, how do I schedule, do asynchronous circuit simulation? There are 2 standard approaches. One I'm going to call conservative, and the other one I'm going to call speculative. They're both used in practice. And in the conservative case, what you do is you say, I'm at time state t minus 1. If my neighbors are all updated to time t, I'm allowed to step forward. So I'm only allowed to simulate as far ahead as my neighbors have sent me information. If my neighbors are updated to time t, I'm allowed to update myself up to time t, but no further, because I don't know if my neighbors are going to tell me something new at time t plus 1. That's called conservative. The trouble with, and that works, the trouble is you can get deadlocks. And so you have to be able to detect deadlocks and get out of it. I'll show you how in the next slide. People have done this before. The other way to do it is to speculate. Is to just say, I'm going to just bet that my neighbor's not going to send me anything. I'm going to simulate ahead as far as I can. But what happens if I'm wrong and my neighbor sends me something? I have to back up. So I have to timestamp my data. I have to keep enough around so that I can back up. And if I'm lucky in my bets, I won't have to do that very often. So that's called speculative or optimistic. And so you can imagine that whichever way you do this, there's also going to be the issue of load balance and locality, either way. And it's often the case that if one part of your circuit is very busy, because everybody is tightly connected, sending stuff to one another, that's where all the work is. You'd like to parallelize that, but that means that you're going to not have very good locality, because you're going to have to take a tightly connected circuit and spread it out across multiple processors. There's no magic bullet here. It kind of depends on the cost of your particular problem to decide how much it's worth splitting up a tightly connected part. So let me tell you about deadlock next. So here is the simplest case. Suppose I have 3 loosely connected ponds. So there they are. So there's a bunch of stuff going on in each of those boxes. And the fish, for some reason, are only allowed to swim, in the directions of the arrows. So suppose now that I've simulated this guy up to time t0, this guy's up to time t0, and this guy's up to time t0. Can anybody take a step? Everybody's waiting for an input to go to time t0 plus 1. Everybody's waiting for everybody else in this circuit. It's a deadlock. So nobody can take a step forward. So how do you get around this? This is what you do. If you've been stuck for a while, you say, something's wrong. And you send out a message to your neighbor, are you stuck too? And if you ever get such a message, you say, something's going on, and you send that to your next neighbors. This guy might say, are you stuck? This guy gets it, are you stuck? This guy gets it, are you stuck? And finally, the message comes back. What happens if you get your own message back that says, are you stuck? You say, there's a deadlock, there's a cycle. I'm going to break it by just going ahead and moving. I know I can do that. So that's how you have to break the deadlock. The trouble is, this can be an obvious serial bottleneck if you have these little tiny cycles in there, right? They really only can go one at a time, and you lose parallelism. And whether that happens or not depends on your particular application. But these are the styles of doing the simulation. So just to summarize, this is the last slide on the discrete event simulation. Everything is discrete in this world. Time is discrete. Space is discrete. I'm going to do domain decomposition, assign my different objects to different processors. I might do some graph partitioning to minimize communication or maximize the load balance, to maximize the locality, so people talk to one another or on the same processor. And I can do it either synchronously, where I have time steps, there's a clock, everybody updates on the clock, or I can do it asynchronously, and I only communicate on demand. And if it's asynchronous, I got this choice between conservative, where I have to wait for inputs up to a certain time and deal with deadlock if it happens, or I can be speculative, just simulate ahead into the future, roll back if necessary if I made a mistake. So that's the end of the overview of discrete events. Any questions before I go into particle systems? So this is a very high-level set of patterns, and I haven't actually told you how to write the code. You're doing a little bit of this in your hands-on session. I've alluded to the fact that there are well-developed tools for this. And so the point is, if this is a well-solved problem from your point of view as a user, don't reinvent. Recognize that some of these problems have been done before. Okay, so the next thing is particle systems. So a particle system has a finite number of particles. They're moving in space according to Newton's laws, typically, and time is continuous. Okay? So here are a bunch of examples, and you can imagine more stars moving around in space under the laws of gravity, simulating electrons, and if you're in Silicon Valley at a manufacturer and you're doing electron beam lithography, you want to simulate the electrons going down the beam. Atoms in a molecule with electrostatic forces if you're doing molecular dynamics. Neutrons in a fission reactor, cars in a freeway, and of course objects in a video game flying around, right? This is probably what most people do it. In fact, a lot of people are doing this in parallel, whether they know it or not, when they play their video games. So let us do some examples about how to do this. So it turns out that the forces on a particle that you're going to use in your F equals ma come in 3 flavors, and they're all parallelized in different ways. There's external forces, nearby forces, and far-field forces. The external force, easiest to explain in sharks and fish, there's an ocean current. The ocean doesn't care where the fish are. It just has a current. Every fish moves depending on its local current. It's all embarrassingly parallel, and it works perfectly well. It also, if you have an externally imposed electric field on an electron beam, everybody knows what the electric field is just depending on their position. Easy to parallelize. The next harder thing to do is forces that depend on your neighbors, but only a few neighbors. So sharks may be attracted just by nearby fish. They don't have to look at fish that are far away. Balls on a billiard table are only going to interact with ones that are close enough where they actually hit. And van der Waals forces. So this is something in chemistry. They are the forces are not like dropped to 0 at a certain distance, but they decrease so fast, 1 over the distance to the 6th power, that people are perfectly happy to simulate that by saying, once they're far enough apart, I don't worry about that. And if you one of my colleagues thinks that's how gecko feet work when they stick to the ceiling and so forth. So this force comes up in lots of simulations. And the most interesting and challenging one to parallelize is when everybody depends on everybody else. And so that's when the fish attract one another, or the planets attract one another by gravity, 1 over r² laws. And so, gravity, electrostatics, radiosity. In fact, anytime you want to solve an elliptic partial differential equation, it kind of has this property that everything depends on everything, but there's some really wonderful mathematical techniques for making it go fast anyway. You don't want to do it in the obvious way. So here is all the code that you need in MATLAB on one page to solve the parallel sharks and fish problem when the only motion is fish in an external current. So I have an array of all the fish positions. So each one is a little xy, says where fish is. So n fish, I have their velocities, I have their masses, everything I need for f equals ma. I have the final time. I'm going to simulate from time 0 to time final. And my algorithm is simply to update the position using the velocity, in the obvious, physics 1 fashion, and update the velocity using the acceleration, and just using f equals ma in the reasonable way. So here's my loop. I'm going to loop over all the time steps. I'm going to start at time t equals 0, and t gets updated by delta t. I'm going to take my array of fish positions and add the time times the velocity. So this is a vector operation, or a totally parallel operation. So here's an array of fish velocities. Multiply it by dt, add that to the array of fish positions. That's embarrassingly parallel. Then I have to compute the acceleration for each fish. There's some function that tells me what is the current, what is the force on me. All I have to know is where I am in the ocean. And then I divide by the masses to get the acceleration. Then I update the fish velocities in the same way by adding a little dt times the acceleration. All that's embarrassingly parallel. So the only thing that's not embarrassingly parallel in this pattern is updating the time step. Because in order to decide what the right time step is, I have to make sure it's small enough to be accurate, but not so small that I don't make progress. And that depends on knowing the largest velocity and the largest acceleration. So this is an array of numbers that's spread out over all the processors. I have to reduce it I have to take the maximum absolute value of all the numbers. So that's a reduction, also a simple pattern, but one you probably don't want to write yourself. It's built in and optimized quite well. So that's the simplest thing to do when you only have an external force. So I think I've said all this. These are the simplest things to parallelize. The force on each particle is embarrassingly parallel. It's the map-reduce pattern. Map corresponds to everybody evaluates the currents independently. The reduced part is, compute the maximum absolute value of all the velocities and the acceleration. So you can pick the time step next. You can evenly distribute the particles across the processors as long as every processor gets an equal number of particles. It's load balanced. Communication is sort of easy, right? It's only the reduction you have to worry about. And so, anyway, enough said about that. Let's go into the harder ones. So now we're going to go on to nearby forces. And this is exactly what your hands-on assignment is about. So you've probably thought about this one already. So now I do have to talk to my neighbors and do some communication. And so the simplest example is collisions. I really have to be close to know that I'm going to exert a force on a neighbor. The simplest algorithm you could imagine, which we gave you last night, is n squared. Every particle, there are n of them, looks at every other particle. So that's n squared, and that does not scale very well. So what are you going to do instead? You're going to use that same idea I told you before. It's called domain decomposition. If all my particles, the green dots, are moving in this square array, and I have 25 processors arranged in this 5 by 5 grid, I'm just going to assign particles to squares and squares to processors. So each processor is going to be responsible for the particles in the little domain that it executes. And so that's going to make the parallelism quite easy, sort of. But I still have some challenges. And so in particular, I need to worry about if I'm in the middle of a domain, like that processor, all my nearest neighbors are also on the same processor. I don't have to do any communication to figure out whether there's a force on me. But if I'm right here, and I'm in this little boundary region, my nearest neighbor could be on the next processor. So indeed, anybody in this little blue boundary zone has to be communicated to your neighbor so they can do the updates and make sure there are no processors there. And so the question is, how do I choose the shapes of these little regions to assign to every processor? It's the same idea as before. I want to have a low surface to volume ratio. Because how much do I have to communicate? It's everybody in this little blue region. That's proportional to the surface area of the part that I own. And I want to have a big volume inside, which means I can update everybody inside without talking to my neighbors very much. So all of the ideas that I talked about before with graph partitioning apply here. Minimize the surface to volume ratio, and so here I would use little squares as opposed to thin slabs. The other challenge is that particles are not necessarily going to be uniformly distributed. And so if I just break up all my squares to be the same size, some of them may be empty, and that's not going to be a good use of my parallel processor. In particular, you look up at the sky, look at the galaxies, that's clearly not uniformly distributed out there when you look up at the sky. And if the electrons are hitting the wall of a device, they're going to be clustered up there as well. And so we're going to have to divide space unevenly. And there's some standard approaches to doing that. And let me just show you a picture of one of them in 2 dimensions. It's called a quad tree. And so I'm going to start with my domain, which is this big square. I'll divide it into 4 subsquares, and I'll look at each one of those and say, am I done? This subsquare only has 2 particles in it. I'll say, I don't have to divide you up anymore. You're going to get assigned to 1 processor. This subsquare, on the other hand, has lots and lots of processors in it, so I'll divide it again into 4 subsquares. These guys are small enough. This one has lots of processors in it, so I only keep doing this division into subsquares while there's still enough particles in each processor. And finally now, all of these squares which have somebody inside get assigned to processors. That's the picture in 2 dimensions. It's called a quad tree. Divide the square up into 4 pieces. And there's a 3-dimensional version called an octree. Divide into 8 cubes. I won't try to draw that picture. Question? Yes?
But in a simulation, the particles will move.
And you have to redistribute it. So in practice, what people do is that they compute this once, and they simulate for a little while. Then they ask, am I still load balanced? And if not, you have to do reassignments. So in particular, once a particle crosses a border, you have to tell your neighbor it's your turn now. You get that particle. And if everybody clusters in one of these, and this depends on your local problem, you may have to rerun the distribution algorithm. And that's a balancing act that depends very much on your particular application. Okay, finally the far field. That's the hardest one, where everybody depends on everybody. And the obvious way to do it costs you n squared. And so the simplest way to do it, when in the MPI sample code that you will have gotten for your assignment, is that you basically have to move every particle no matter which processor it starts in. So here I have 5 processors arranged in a row. And everybody has to be everywhere. So at the beginning, every processor just looks at its local guys and computes all their contributions to one another. Then each processor packages up everything it owns and sends it to its neighbor. And so now this processor has a copy of its left neighbor in itself. It computes all their interactions. Everybody does that. Then everybody sends them to the next neighbor, and after 5 steps here, every particle has visited every processor, and every interaction has been computed, and this is the naive algorithm, and you're done. But it is way too expensive if you can do something better. Okay? So in order to do better than having everybody visit everybody, we have to use some mathematical properties of the forces. We have to take advantage of the fact that in real life, when 2 particles are far apart, the forces between them are not, get smaller, they get simpler in some way. So here is the right analogy. So imagine you want to compute the force on the Earth from all the stars in the galaxy, or all the stars in the universe, whatever you can see. So you walk out at night and you look up at the sky and you see a few billion little white dots, and you think, okay, I have a few billion points that have to interact with one another. And then you realize that one of those little white dots that you see is actually the Andromeda galaxy. And it has a few billion white dots inside of it, and you figure, oh, do I have to do all those too? No. Approximating the Andromeda galaxy by a single white dot at its center of gravity with the total mass is a really excellent approximation to the force of the gravity of all of Andromeda on the Earth. And certainly when Newton saw the apple fall, he didn't worry about every rock in the Earth. He also approximated things by single points. So it turns out that by being systematic about that, because just like the Andromeda galaxy looks like a point to us, the Milky Way looks like a point to the Andromeda galaxy, you can drop the complexity from n squared to order n, or order n log n, if you count more carefully. And so this is a deep mathematical fact. It got the inventors of it into, the 2 inventors into 3 national academies. It's a widely adopted method called the fast multipole method. There are actually 2 approaches. One of them works by taking all the particles and saying, well, if I move them just a little bit, I'll get almost the right answer. And so if I take each particle and move it to the nearest mesh point, so they live on a little mesh, you can solve the problem if it happens to be gravity and electrostatics by using the fast Fourier transform. And people often do that. That makes it go a lot faster. But if it's a more general problem, then what you do is, as I said, you approximate each cluster of points by its value by a new point, a metaparticle. It's at its center of gravity with its total mass. And if it's far enough away, that's a good enough approximation. And so those are called tree codes. And as I said, those are also widely adopted. And they drop the complexity from n squared to order n or n log n. And these have also been parallelized in great detail. Okay, so that's the end of doing particle systems. So I talked about the external forces, the easy ones. The nearby force is a little bit harder. And then the far field forces, which require some deep analysis to get it right. So are there any questions about particle systems before I move on to lumped systems or ODEs? Let me get a drink of water. Water is legal in this room, so, especially for the speaker. Okay. So lumped variables, if you like. So many systems are approximated this way. I mean, if you've had sophomore calculus, this should come as no surprise. I have a whole list of variables that are sort of describe some values that I want to compute. Each one depends on some continuous parameter, like time. And so a circuit, again, to be an electrical engineer, is the most obvious example. I'm going to approximate it by a graph. The wires are going to be the edges of the graph. The nodes are where the wires come together because I have a connection. And each edge has some electrical component along it. There may be a resistor, a capacitor, inductor, a battery, whatever. And so why do I call this a lumped system? It's because I'm not worried about where all the electrons are or the voltage along every point in the wire. I just want to know the voltage and the current at each node. So just a finite short list, hopefully short list, of points in the circuit where I'm going to write down some equations to say what's your voltage there, what's your current there. And when you write it all down, you get a system of ordinary differential equations with respect to time. And sometimes, in particular for circuits, it's a little bit more general than differential equations because you have some algebraic equations in there too without any derivatives in it. And the typical example says, the sum of all the currents going into a vertex is equal to the sum of all going out. That's one of Kirchhoff's laws. That's just a sum of values equals 0. It's not, there's no derivatives in it, right? So you can have a mixture of equations with and without derivatives. So let me just show you that example to be specific. So again, for circuits, I'll have a non-circuit example in the next slide. So I have a finite list of values of the voltages at the nodes where the wires come together, and they're all functions of time. I have a finite list of variables which tell me how the current, the amps going down each wire. And I also have the branch voltages, the difference between the voltage at one end of a wire and the other one. And so I just write down all the equations you learn as an electrical engineer that describe all the relationships between these variables. So A is this big sparse matrix. Most of its entries are 0. It simply says who's connected to whom, which wire is connected to which other wire. So it's just a bunch of 1s and -1s for every wire, but it's mostly all 0s. And so the first equation just says A times the current equals 0. That says that the sum of the currents going in is equal to the sum of the currents going out. Write all those down. Then you write down a similar thing for the voltages. You write down Ohm's law. No derivatives yet. Finally, I get to some derivatives, which are how capacitors behave and how inductors behave. And this huge system is my system of ordinary differential equations and algebraic systems. And the pattern that we're going to have to deal with here, and I'll be more specific, is I have to work with sparse matrices. So I have to do operations on sparse matrices and make those run in parallel. So A is a sparse matrix. This is even a bigger sparse matrix. So here's another example that my colleagues in another building do, structural analysis. You may remember one of these freeways collapsed during an earthquake. So there's lots of rules in California about doing very large-scale finite element analysis of any structure that gets built to make sure it's safe. And so you write down another bunch of big equations, except it's not Kirchhoff's laws anymore. It's Newton's laws and Hooke's laws, spring constants, stuff like that. And so what do you do? What are you required to do? You push forces onto that mathematical model, and you ask, is it going to fall down in an earthquake? And so this is important to all of us who are in one of those buildings that's been modeled this way. So there's two kinds of ways of doing it. You can either do dynamic modeling, which is, you put in some measured input that's from an earthquake, and you ask what happens to the building. The other thing that comes up often is an eigenvalue problem. So matrices not just describe differential equations, they have eigenvalues, resonant frequencies if you prefer. And so the question is, from historical data, we know that earthquakes have certain resonant frequencies. They shake at certain values. And springs and buildings have certain frequencies at which they go into resonance. And the question is, does the earthquake frequency match the resonant frequency of the building? Because if it does, the building is going to go into resonance and fall down. And so you have to make sure the eigenvalues do not match. And so those are big computations that people do too. And that also uses the same patterns, sparse matrix operations, and they're parallelized in very similar ways. So let me give one more example here. Hold on. Oops. Okay. Let's hope this plays. There we go. So anybody who plays this game on an Xbox 360 is doing real-time parallel finite element simulation of whatever, stone or steel or wood. And this was all running in parallel, so the system builds a model of the entire game-playing region. And everything you see flying around is doing F equals ma in parallel, including all the smashing and things breaking. So let me just scroll ahead a little bit to some of the other features. You can watch the whole video yourself at some point. So stone has particular material properties you have to get right, so it fractures in the correct way. Glass is slightly different. And the sound effects are also done by simulation, right? The stuff is vibrating. So let me just scroll. Oh, metal. All right, so metal behaves somewhat differently. So it bends in particular and is pretty stiff, so you got to work pretty hard to get the door to close. And let me just go ahead. Oh, plants. So you can do soft materials as well, and they kind of vibrate around a little bit. And not even Darth Vader can smash everything. You can only knock the bark off of that one. So wood is a little bit more complicated because there's a lot of elasticity in it as well. But let me move ahead to so you can sort of see what the programming environment is here. So there's the example of what the discretization looks like. It doesn't have to be very fine for this to happen. The graphics, has to obviously be much finer, but this is what the discretization looks like. And you can also change the physical parameters. So if you want to have a nice, juicy wall that bounces around, you can just change the Young's modulus and it all works. Anyway, so you can, and all of this has been successfully parallelized. Okay. Oops. Stop. Let me go back. Okay. This is work of my colleague, James O'Brien. Okay, so in all these examples, and most others, the matrices are sparse. So you don't want to, so that means almost all the entries are 0, and we don't want to store those zeros, and we don't want to compute on them. And so and why are they sparse? It's because in a physical system, each component only depends on a few neighbors in some sense, right? And that corresponds to the few non-zeros that are in the matrix. And so the question is, how do I take advantage of that sparsity structure to write down an algorithm? And what are the common features of how do I parallelize it? So let me just give you two examples, which are explicit methods and implicit methods for solving a really, really simple differential equation, and just say which patterns arise. Eigenvalue problems use the same patterns. I won't go into those details. Okay, so let's suppose I'm trying to solve x dot equals a times x, right? So a is a column vector, a is a big sparse matrix, and so I'm going to discretize it. I only want to know the values of x at certain time steps, 1, 0, 1, 2, 3. And so what does my differential equation tell me? It basically tells me the slope of the curve, right? So a times x is the slope of the curve. And so to get the value of the solution at step I plus 1, I take the value at I, add the time step times the slope. So the question is, where do I evaluate the slope? And you get two different parallelization schemes depending on that. There's explicit methods and there's implicit methods. The simplest thing to do is to evaluate the slope at step I. And so I just plug in the slope is a times x. Here's my formula for updating. I take my vector, I do a matrix vector multiply times by sparse matrix and add it to update. Sparse matrix vector multiplication comes up everywhere. There are lots of clever ways to parallelize it. You should think of this as a previously solved problem. The other thing you can do is say, there's some mathematical limits to doing this. You have to take very tiny time steps sometimes. So what some people do is say, I'm going to use the slope at the other end of the time interval, not at step I times delta t, but at I plus 1. So my slope depends on the value I don't know. If I plug that in, I can still get an equation to tell me what's the solution at step I plus 1, but to do it, I have to solve a sparse system of linear equations, where the sparse matrix is mostly A. So that's the other pattern that comes up over and over again. And so we have to solve sparse systems of linear equations. Again, a well-solved parallelized problem. And so either one you may want to use. It depends on the physics of your problem. The explicit one is much simpler to parallelize, but I may need tiny time steps. The implicit one is more expensive, you'll see, but I can take much, much larger time steps. And eigenvalue problems are the same components. So let me just sort of give you, so I will come back later and tell you, what tools there are for solving these sparse systems of equations. But let me, before I do that, tell you one other place they arise, which is like the most, which is our last example in our 4, going from most discrete event systems to continuous systems where everything is parallel. So PDEs. So these come up all over the place in modeling. So they come in 3 flavors. Elliptic problems, so if you haven't had a course in this, don't worry. I'm not expecting you to have a lot of mathematical background. The whole point is to see simple patterns. That comes up in electrostatics or gravity. The answer is the potential depends on the position everywhere else. Every point depends on every other point. That's hard. The next sort of simplest thing is when you have wave equations. They're called hyperbolic. So everybody only depends on their nearest neighbors because waves only move at a finite speed. So the answer, like the pressure of a sound wave, just depends on your position and time, but you only have to know what happened at your neighbors. And then harder is parabolic equations. They depend on time, but everybody depends on everybody. And that's the case of heat and diffusion. So the answer is a function of both position and time. And so this difference here between local and global is enormously important when you try to parallelize it. Global means if everybody depends on everybody, so there's either a lot of communication or tiny time steps or one of those really clever algorithms I told you about before. And local is when things move at a finite speed. Sound moves at a finite speed and so forth. That's going to limit your communication. And of course, in the real world, like fluids, elasticity, you combine these things. But I'm just going to talk about the model problems. So I'm going to just write down what equation arises for solving the heat equation on a one-dimensional bar. So here I have a steel bar. One end is in the ice, and it's blue. The other end is in fire, so it's red. And so the color tells you the temperature. I want to write down the equation for the temperature as a function of position x all the way along that bar between 0 and 1. And the famous equation that Fourier wrote down an awfully long time ago says the rate of change of the temperature, U is the temperature at position x time t, is proportional to the second derivative of the temperature with respect to x. So I'm not, so if you've seen this before, good. If not, don't worry about it. I'm going to discretize both space and time. I'm only going to ask what's the temperature at a finite number of equally spaced points. And I'm only going to ask for the temperature at a bunch of equally spaced time steps. Time equals 0, delta, 2 delta, 3 delta. And so when I write that down, it turns out that if I know everything at time step t, and I want to go to t plus delta t, I have to solve a sparse system of linear equations. It's almost exactly the same as before. So I have my answer at time step I. I know that. I want to get the answer at time step I plus 1. I have to solve a system of linear equations. Here's the matrix. And it's very, very sparse. And it's basically, this is the matrix, right? It's a very famous matrix. It's called the Laplacian. 2's down the diagonal, minus 1's, and I have to jiggle it a little bit. But basically, that's it. So solving a sparse system of linear equations. That was the 1D case. If I want to do it in the 2-dimensional case, so I have a plate, a square plate, then I can do all that math again. I get another sparse matrix. And it reflects who's connected to whom. Everybody depends on its 4 nearest neighbors. And so every row, has 4 non-zeros in it. They're my left and right neighbors. Here's my top neighbor and bottom neighbor. So again, I get a sparse matrix. It reflects the fact that I'm only connected with my neighbors. And so I need to solve that system of linear equations. And so what I'm just going to do is give you a little tour through the algorithms. I'm not going to tell you how they work today. In fact, I teach a whole course on this. But the point is, there's parallelism that you should recognize in each one. And so I'm just going to give you a list. I'll tell you the algorithm. And I'm going to order it from most general, solves any system of linear equations, to very specialized, is only good for the matrix I had you on the last slide. But it's going to go faster and faster. This is often happens in my office hours. Somebody comes in and says, I need to solve a system of linear equations. I said, well, that's fine. Just use Gaussian elimination. It works fine, costs you n cubed, works in any old matrix. And they tell me that's not fast enough. I said, well, tell me about your problem. And they say, oh, I forgot to tell you, it actually has a lot of zeros in it. It's banded. It only has non-zeros near the diagonal. And they tell me how wide the band is. And I say, oh, there's another algorithm for you. You should recognize it. The cost goes from n cubed to n squared. You should be very happy now. And they say it's still not fast enough. And I say, okay, well, tell me more about your problem. And they say, well, it actually is only, has this connection with its nearest neighbors, and it has a certain property called not being too badly conditioned, which is not the topic of this course. And I say, well, you haven't told me enough. I have another algorithm that uses a lot less memory. I can go from n to the 3 halves down to order n, but it's still going to cost you n squared time to do it. And then he says, well, I'm actually going to solve it over and over again, the same matrix. Can I take advantage of that by just computing the inverse once and using it over and over again? I say, nah, still going to cost you n squared time. That doesn't help. And then they tell me, oh, I forgot to tell you it's symmetric. And in fact, it has this nice property that all its eigenvalues are positive. It's positive definite. I said, well, why didn't you tell me? There's another algorithm. I can get your complexity down from n squared to n to the 3 halves. And again, it's not so hard to parallelize. And they say it's still not fast enough. Then I say, well, there's this other algorithm called red-black SOR. That works sometimes. I can do Gaussian elimination on it if it's sparse enough, and yours is sparse enough. I can do all that. And they say it's still not fast enough. And then I say, well, what are you really trying to do? Well, I'm trying to find the temperature on this square plate. I said, why didn't you tell me? You're trying to solve Poisson's equation. There are lots of great algorithms for Poisson's equation. I can do it with the FFT. It costs you only n log n. Or there's an algorithm called multigrid. It's order n. Your answer is of size n. This is optimal, right? You can't do better than order n to get the order n answer, and it can be parallelized well. So the point of this is you have to know a certain amount of structure in your problem to pick the right algorithm, and then each of these is parallelized by using one of those 7 dwarfs that I told you about. And I'm not going to have time to tell you about all these mathematical properties. As I said, I teach a whole course in this, and you're welcome to take it when I teach it this next semester. Okay. And it all happens in 3D, too. It's the same list of algorithms. It all generalizes to 3D. The complexities change a little bit. Okay. And this is how, again, I'm not going to do this today, all of those algorithms that are on the previous slide are all built out of those motifs, those 7 dwarfs that I told you about. All of these have been well studied, how to parallelize them. And your first resort should be to say, which one of these solvers do I want to use, and which one of these 7 dwarfs is the right way to parallelize it. And some of this will be the topic in tomorrow's talk. Today we're just trying to recognize the patterns. Tomorrow we're going to talk about how to make them go fast. So Kurt is here. I'm almost done. Let's see, I have 5 more minutes. We're on good time. So all the pictures I've showed you so far have been for a nice regular mesh. Everybody's talking. They're north, south, east, and west neighbors. Most real-world problems aren't quite that regular, but all these ideas generalize. So let me just show you some pictures to say how they generalize. So this example is in MATLAB. You can just ask for the NASA Airfoil in MATLAB, and it pops up this picture for you. And so this is the mesh that you get when you try to simulate airflow over a wing. So these are little finite elements. Each one is connected to its neighbors. And you write down a system of equations, and the connectivity here tells you what the sparse matrix looks like. And if you write it down as a matrix, this is what's called its spy plot. Every little black dot is a non-zero. And if you put things in a reasonable order, everybody is only talking to its nearest neighbors. The trouble is that when you do Gaussian elimination on this, you get a lot of new non-zeros. And here's what the matrix looks like after you finish doing Gaussian elimination. And it's filled in a lot. So part of the problem is, how do I fix that? And there's one answer. I've already told you what it is. It's that graph partitioning algorithm that I told you about, which minimizes communication. It also happens to minimize the filling. So that one problem solves both. That one algorithm, graph partitioning, solves both these problems. Here's another example, which has actually motivated one of the problems in the PARLAB. So here, the biomedical problem here is that elderly people with osteoporosis, it's hard to predict when they're going to actually break a bone when they fall. The standard model is to measure their bone density and say if it's above a threshold, then you're okay. If it's below a threshold, you have to be careful, take certain medicines. That's not accurate enough. And so what my colleague, Tony Kevney, tried to do, and has now a startup doing this, is to find a better way to predict it. So it began by taking a bone, a real bone, human bone, from a cadaver, putting it in a micro CT scanner, and scanning it with much too high radiation for a living person, getting a 22 micron resolution 3D model of all the bone structure inside that vertebrae, and creating a finite element model of it with 500 million unknowns that exactly describe the strength of that vertebrae. And so what you can do is take that accurate model of the vertebrae and start crushing it, pushing on it in the same force, exerting the same forces that would happen if you fell down or tripped or whatever, and ask, would it break? And so then they compared that to the measurements in the laboratory. They actually took the vertebrae and pushed it, and it broke at the same time. It was a much more accurate way of measuring the likelihood that an osteoporosis patient is going to need treatment. And they won the Gordon Bell Prize for this in 2004, which is a big prize for doing a big supercomputer simulation. So this ran on one of the biggest supercomputers in the world. That's not a commercial application. One of the things that they're working on now is doing a much lower resolution problem. But this is one of the applications that comes up in parallelism. And my next to last slide, here's another place where it comes up, where the meshes are actually changing in time. So here's a simulation some colleagues at LBL work on, where you have an exploding star or anything that's exploding, a flame front. And so there's something burning right here. This is completely combusted. This is unburnt. Here is where all the action is happening, all the chemistry is happening. And of course, it's moving as the flame front moves. So you have to have a very, very fine mesh where you're solving your equations out here. And you have to resolve that finally because the chemistry is complicated. Out here, you don't need to spend much time computing because it's nice and smooth. And so what you have to do is change your mesh dynamically over time as it moves. This makes things even more challenging, and there's lots of projects where people have actually done this and parallelized it using the tools that I have, that I've told you about and will be telling you more about tomorrow. So finally, the last slide, just to remind you of what common problems we've seen. Finding parallelism in locality, right? Both of those are critical to get things to work. We had to worry about load balancing. Sometimes we could do that statically. We have this nice model called graph partitioning. It applies to many problems. Sometimes we have to do it dynamically. If the problem is changing over time, you may have to reload balance during the jobs. Linear algebra came up all the time, both dense and sparse. You'll hear more about that tomorrow. And there's some very clever algorithms for pushing particles around that change the obvious cost from n squared down to n log n. And again, you'll hear a little bit more about that tomorrow. So that is my last slide. The next talk is going to be the next level of patterns, which Kurt is going to talk about, which is how you take pieces like this, which have been well parallelized, and glue them together to create to compose them to create a much larger application. Structural patterns. So, are there any questions before it's Kurt's turn? Okay. There's a lot of material in here, so I'm happy to take questions whenever they come up. So, you ready, Kurt? Okay, great.